Hi, welcome to the types of nuclear reactions. This is a sorting activity. And in this activity, we are going to learn about different types of nuclear reactions and categorize these reactions here as either fusion, fission, transmutation, or a type of radioactive decay. And we're going to first start by looking at fusion, fission, and transmutation. Now, before we go into that, I just want to point out that these cards here that we're looking at are showing nuclear reaction equations. And just like in math, where an equation is separated by an equal sign, in chemistry, reaction equations are separated by an arrow. It's that little arrow in the middle there. On the left side of the arrow, you have what you're starting off with, since we read from left to right. Those are your reactants. And on the right side of the arrow, that's what you end up with or make. Those are known as your products. And we're going to pay close attention to the reactants and the products that we have in our reaction to help us identify the types of reactant. So let's get started. During a nuclear reaction, the nucleus changes by losing and or gaining protons, neutrons, and or energy. Now, before I go on, I just want to point out the symbols for protons and neutrons, because I think this is important for you to understand. We know that in an element symbol, the top number on the left side would be your mass number, and the bottom number is your atomic number. That mass number represents the mass, or describes the mass of the atom, and the bottom number, the atomic number, represents the number of protons inside of a nucleus. When we're dealing with these particles, these numbers have similar but not the same exact meaning. So the top number, when I talk about a particle, these are not elements. These could be subatomic particles like protons, neutrons, and electrons, or other particles we've not seen before like gamma particles or beta particles. And you'll see more of those later. But I just want to explain what the numbers mean. The top number still describes the mass. So if we talk about a proton, we know a proton has a mass of 1, approximately 1 AMU. And the same thing with a neutron, it has a mass of approximately 1 AMU, so the top number will be 1. On the other hand, if we look at something like an electron, if I go down here, electrons have an approximate mass of 0, so their top number will be 0. So that top number still is describing the mass. But when we talk about particles, it's not the number of protons plus neutrons, it's just whatever the mass of that particle is. The bottom number, on the other hand, instead of describing the number of protons or the atomic number, what it describes is the nuclear charge, or the charge of that particle. Now, what do I mean by that? We know that protons have a +1 charge. And so because protons have a +1 charge, the number here for a proton will just be 1. Neutrons are neutral, they have no charge, so that number is 0. Because what this is telling us is, well, what charge does this particle contribute to the nucleus? Protons, 1, and neutrons, 0. On the other hand, if you have an electron that's injected into a nucleus or is ejected from a nucleus, electrons have a -1 charge. So you'll notice that the bottom number is -1 for that particle. All right, so let's get back to what we're talking about. So during a nuclear reaction, the nucleus changes by losing and or gaining protons, neutrons, and or energy. So this often results in changing the identity of the element in a process called transmutation. Now, when I say the identity, we're normally talking about protons. Protons are what identify it. But you can also change the isotope itself by changing the mass. Now, nuclear reactions often generate lots of energy, and there are two types of very high energy reactions. There's fusion and fission. So let's talk about fusion, for example. Fusion means to bring together. So when you think about fusing something, you're bringing something together. And that's what happens in a fusion reaction. Fission, on the other hand, is the opposite. With fission, you're splitting things apart. And I like to think of when you open up a can of soda and you have all these bubbles that are breaking off of the surface of the soda. That's what I think of fission, like fission, fizzy. So it's sort of breaking apart or splitting apart. So that's what this is saying here. The color coding is off. I'm sorry about that. But fusion reactions, you have 2 or more nuclei combined to make a larger nucleus. And that part's important, that you're making something larger. Whereas fission, you're starting off with a larger nucleus and it splits apart into 2 or more smaller nuclei. Now, sometimes these fission reactions can happen spontaneously, meaning on their own, And other times, the fission reactions are initiated by particles like neutrons that are propelled into the nucleus at high energies. Now, you can kind of think of it when if you're playing pool. I don't play pool, but I've seen it on TV, and you have those, your pool balls are sort of lined up, and you break the pool balls with another pool ball. That's what that neutron is doing. It's sort of breaking apart that nucleus. But it's not a nucleus itself. It's just to initiate the reaction. And so if you have a fission reaction that needs a little help getting started, you can shoot a neutron into it. So let's go ahead and see if we can use those terms to figure out what's fusion, what's fission, and what's transmutation, or something that if it doesn't change, we'll just leave it outside. Okay, let's take a look at the first one here. So if you take a look at that first one, card A, you're starting off with one thing, polonium-239, and you're forming two things, uranium-235 and helium-4. So what do you think that is? Is that fusion, fission, or transmutation? Well, it's definitely transmutation. There is a change there, but let's be a little bit more specific. If you're starting with one thing and you're breaking it apart into two or more things, that would go under fission. So I'm going to put card A under fission. Now, how about B? Well, we're starting with carbon-14 and we're making nitrogen-14, and this is called a beta particle, by the way. But let's say you didn't know that. You're making this other particle here. Okay, so what is that? Now, looking at this, you may think, oh, this is fission. We're starting with one thing and we're splitting it apart into two or more things. But here's the thing. Remember, with fission, you have to be, when you split it apart, you're taking something larger and splitting it into two or more smaller nuclei. A beta particle is not a nucleus, and you didn't make anything smaller from it. Okay? So this one, you did change it, however. We're going to put it under transmutation. You are splitting it, but you're not making anything smaller. Whereas here, polonium-239 is what you're starting off with. You made two smaller nuclei, uranium-235 and helium-4. All right, let's take a look at C. If we look at C, we have 137, barium-137 with a star. That star just means it's super excited, has a lot of energy. And we made barium-137 and this particle here, which is called a gamma particle, by the way. Okay, well, take a look at it. It looks like you're taking one thing and splitting it apart into two things. However, what do you notice about this? One, did we make something smaller from the barium? Nope. The mass number is the same, so it's not anything smaller. What about, did we make something different? We start off with barium-137 and we still have barium-137. No, we didn't. So this we're going to leave out because it's not fission. We didn't make it into something smaller. And it's not transmutation because it didn't change. It's still barium. So let's take a look at D now. We have hydrogen-1 and hydrogen-3. And they're combining together to make helium-4. What would that be? That's right. That's fusion. So we're going to pop that one over there. All right. How about E? We take a look at E. We look at this one. We're starting off with, this is a neutron, and we have uranium-235, and then a bunch of other things. What do you think that is? Now, if you're thinking, wait a second, we have two things, and then we're making a bunch of other different things, well, that will go into transmutation. That's actually not quite correct. Because remember, a fission reaction involves taking a larger nucleus and splitting it into smaller nuclei. And that can be initiated by a neutron. A neutron is not a nucleus, right? A neutron is just a particle to get that party started. So with that being said, this would still be a fission reaction. It's just a non-spontaneous fission reaction, one that needs help from a high energy neutron. So when you're trying to figure out if it's fission or not, ignore the neutrons on the left-hand side. Okay, take a look at F. We have oxygen-14, fluorine-18, and forming silicon-28 and helium-4. Well, these are clearly going under transmutation. I definitely changed things, but I'm not starting off with one thing and splitting it into two or more smaller things. Or starting off with two things and making one larger thing. So that will go under transmutation. Let's take a look at G. We have polonium-218 and lead-214, plus an alpha particle, which, by the way, is equivalent to a helium-4 nucleus. So where would this go? You got it. It goes under fission. You have one larger nuclei splitting into two or more smaller nuclei. An alpha particle is a helium nucleus, so that works. How about the next one, H? Right, that is transmutation. You are changing the mass numbers of the different elements. Even if you haven't changed their identity, there is a change there. How about this next one? We have potassium 42 forming calcium 42, and this is also a beta particle, which you'll see later. Okay, so if we take a look at this one, we think, we're taking one thing and we're splitting it into two things. Maybe that's fission? This is not smaller. The calcium is not smaller than the potassium. So that won't go into fission, but it would definitely go into transmutation because we definitely changed it. All right, take a look at this one. Oxygen 16, helium 4, and neon 20 to make neon 20. Definitely a fusion. Radon 222, forming radon 222 in a gamma particle. Well, it looks like we're splitting things apart, but there's no change in the mass and no change in the identity. We're just going to leave this one out of the boxes. And now we have lithium with a neutron and helium 4 to form helium 4 and hydrogen 3. What do you think about this one? That's right, another fizzy fission. Remember, that neutron is just getting the party started. All right, so what we've done so far is we have sorted them by fusion, fission, transmutation, or we have this sort of extra box for later. Now what we're going to do in the next video is talk about radioactive decay, because what we'll do next is we'll sort the rest that we have left, and we'll also sort some of the ones that are in fission and transmutation into the radioactive decay.